Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on February 2nd, 2026, just 2 days ago. It reveals that multimodal large language models can effectively understand source code rendered as images, achieving up to 8 times compression without losing semantic meaning. The paper is titled CodeOCR on the Effectiveness of Vision Language Models in Code Understanding. And as we'll see shortly, the way these models leverage visual cues like syntax highlighting opens up a completely new avenue for efficient inference. And for those interested in the implementation, the authors have shared their code on GitHub. Alright, Figure 1 illustrates exactly how this visual compression works compared to traditional text. On the left, we see the standard text-only sequence, which breaks the code into 110 separate tokens that the model reads sequentially. In the center, we have the same code rendered as a high-resolution image, which initially requires a similar token budget. But looking at the right panel, we see the power of this method. By adjusting the resolution, the image is compressed to just 27 visual tokens. This achieves a 75% reduction in size, while keeping the code legible for the model. So, while Figure 1 showed the compression potential, Figure 2 now breaks down the pipeline that makes it possible. It starts at Stage 1, on the left, where the model accepts both the rendered code image and a standard text prompt. In Stage 2, the image is split into patches for the visual encoder, running parallel to the text tokenization. Next, Stage 3 employs A versus L adapter to align those visual embeddings with the text space. Finally, Stage 4 fuses everything in the MLLM backbone to generate the answer. Okay, with the pipeline defined, Figure 3 maps out the experimental design and the 5 core research questions. At the center, we see the 4 downstream tasks: summarization, completion, clone detection, and question answering. The top left panel, labeled RQ1, compares the image-based approach against raw text, confirming they achieve comparable results. Across to the right, RQ2 investigates resilience, testing how well models handle compression ratios from 1x down to 8x. Next, the middle panels explore visual strategies and language generalization, while the bottom section, RQ5, analyzes how information degrades under heavy compression. Well, having outlined the tasks in Figure 3, Table 1 now provides the concrete statistics for these benchmarks. The first 2 rows highlight code summarization and code completion, which are particularly demanding. Notice the average context length column here. These tasks require processing over 6,000 tokens per example. This heavy load is exactly where visual compression becomes valuable. In contrast, the third row shows that code clone detection operates with much shorter contexts, averaging fewer than 200 tokens. So, Table 1 set the stage with the datasets, and now Table 3 presents the main performance comparison across all 4 tasks. The columns here group results by input type, no context, standard text, and image. What immediately stands out are the green highlighted cells, which mark instances where the visual approach outperforms raw text. For example, look at the code clone detection column for GPT-5 Mini. The image input boosts the F1 score significantly, jumping from about 33% to 47%. We see a similar trend in code completion, where the Gemini 3 models achieve consistent gains using visual inputs. Alright, while Table 3 established the baseline, Figure 5 tests resilience under heavy compression. The charts plot performance as we reduce the visual token count from 1 down to 1/8. Notice the red and yellow lines for the Gemini 3 models in the code completion panel on the top left. They remain remarkably flat, suggesting these models effectively denoise low-resolution input. In contrast, look at the pink line for GLM46V in the bottom right question-answering plot, which drops sharply as quality degrades. Interestingly, the middle column shows that for clone detection, some models actually improve at moderate compression, likely because blurring removes distracting syntactic details. Wrapping up, the big hook here is that image-based processing offers a viable path to efficiency, cutting token costs by up to 8 times while maintaining accuracy. This suggests a paradigm shift where future coding assistants might rely on pixels rather than text to handle massive software contexts. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.